Hi there, Rachel Chase here, and in the second part of our discrete probability distributions video, we will explore binomial probability specifically. A binomial probability distribution is, for starters, a probability distribution which we learned about in part 1, and binomial implies that there are only two things exactly that could happen. For example, flipping a coin, there's only two possible things that can come out, heads or tails. Gender of a child, boy or girl, two things. So we said two things can happen. If you're looking at something in terms of pass or fail, that would also be binomial, late or on time, or perhaps even early, right? So if you're looking at it as just later on time, it's binomial. If you are considering other options, like how late is somebody or how early are they, then that would not be considered binomial. So things we've explored in the past that are not binomial, for example, would be rolling a fair six-sided die, because there are 6 outcomes to that as opposed to 2. To calculate binomial probability, we have the formula, and this uses combinations, which we learned about in chapter 4. So the probability of event x occurring is equal to n choose x, p to the x, q to the n minus x. Q is always equal to the complement of P. So if P is 0.2, then Q would be 0.8 because I have to add up to 1. The mean of a binomial distribution is given by the formula n times P. So it's your sample size times the likelihood of occurrence. And the variance is equal to n times P times Q, of course, which means the standard deviation is the square root of that amount. It really is much simpler to calculate the mean and standard deviation of a binomial probability distribution than just a regular probability distribution. However, it's not really a big deal, right? Either way, it's something that's calculable. Let's take a look at an example here. There are 5 flights daily from Pittsburgh via U.S. Airways into the Bradford Regional Airport in Bradford, PA. Suppose the probability that any flight arrives late is 0.2. In the previous video, we learned that when they ask you what you would expect to happen, that's a fancy way of asking you for the mean. So here, they've told us we have 5 flights daily, which means that our sample size is n equals 5. This 0.2, the probability that it's late, is p. So p is 0.2. And although we don't need it yet, that means that q is 1 minus 0.2, which is 0.8. How would we calculate then the mean? Mu is equal to n times p, which is 5 times 0.2. That gives us 1. So we would expect on any given day for one flight to be late. The standard deviation is given by the square root of n times p, so that's 5 times 0.2, times q, which is 0.8. So that's the square root of, this is 1 times 0.8 is 0.8, and then just calculate that. So find our square root of 0.8. Gives us 0.894 when we round. Now, if instead you wanted to find out the probability of a certain situation occurring, so for example, what is the probability that none of these flights are late? This is where the formula for p of x comes in. This is asking us find the probability when x is equal to 0, in other words, none, that means 0, flights are late here. So we learned on the previous slide with formulas on it that that would be 5 choose 0, since it's 5 flights, so n choose x. P is 0.2 to the x, which is 0. Q is 0.8 to the n minus x. 5 minus 0 is 5. From here, there are multiple ways to approach simplifying this. You can do this one step at a time, or you could type this in your calculator all at once, and later I'll show you a trick using a function that's pre-programmed. If you want to type this in your calculator all at once, you'll do it as follows. 5, math, go to your probability window and select option 3. It's always a combination here with 0. Then you have 0.2 to the 0 power and 0.8 to the 5 minus 0, which is what gave us 5 here. This would be probably the most efficient way to go about it, is typing it in all at once. Then you don't have to worry about any crazy decimals or rounding, etc. So if you did want to round your final answer here, what would be acceptable? At a minimum, 3 decimal places. This is a terminating decimal, which is kind of nice in this case. But if we chose to round, that would be 0.328. So what's the probability that none of the flights are late? About 32.8%. That's not too bad. What if instead we asked for the probability of exactly one flight being late? Well, then we can repeat that formula, but replace 0 with 1. We're looking for the probability that x is equal to 1, which means we have 5 choose 1, 0.2 to the 1, 0.8 to the 5 minus 1 is 4. So if we go back to our calculator, do what we just did, 5, choose 1, 0.2 to the first power, 0.8 to the fourth power, which gives us 0.4096. So what's the probability that one of those flights is late? Well, here's the catch is we don't know which flight is late, right? It could be the first flight that's late or the second flight, so on and so forth. So what this does is the 5 choose 1 portion figures out how many different ways could one of those flights be late, and then calculates the probability from there. So that probability is approximately 0.4, if you round to 3 places, that ends up being 0.41, or just leave it as 4096. My personal opinion is anytime you have a terminating decimal, avoid rounding if you can, especially if you were planning on using this for another question. So on the next slide, you'll see how we use these to answer multiple step questions. Now, again, I just want to illustrate here because it's a little confusing. In Chapter 4, we talked about using the complement rule to answer questions like, what is the probability that at least one flight is late? And we said, well, you know how to calculate the probability that 0 flights are late, and the reason for that is you don't have to concern yourself then with which flight it is. But if we're talking about one flight being late, you don't know if it's flight A, B, C, D, or E. It could be any one of these. So what's the probability that one flight is late? That means 0.2 to the first, 0.8 means on time, to the fourth. And then this part, again, 5 choose 1 tells us it could be the first flight, or the second flight, or the third flight, or the fourth flight, or the fifth flight. So this deals with the number of ways that a flight could actually be late, and then this is the probability of occurrence, which is why we multiply those together. Now let's take a look at how these apply to cumulative statements. Same question, but now, what is the probability that at least one of these flights are late? So we've learned in Chapter 4 how we could calculate something like this, and you don't actually need to know how to calculate a binomial probability to answer the at least one question. But think about what this is saying. What's the probability that x is at least is denoted greater than or equal to 1? That means what's the probability of one flight being late, or 2 flights, or 3 flights, or 4 flights, or even 5 flights. But again, when you see at least one, there's a major shortcut which will save us a lot of time, and that's using the complement rule. What do we not consider here? And that's the probability of 0. What's the probability that 0 flights are late? Well, we calculated that on the previous page. Now, if you're curious, is there a quicker way? If you're using the technology, there is a much faster way to calculate binomial probability, and this is acceptable for use if you'd like. If you look under your distribution menu, it's above the vars key, and scroll down, you're going to look for something called Binomial PDF. Binom stands for binomial. PDF stands for probability density function. That's not something you have to know. For our purposes, you're only going to select the first one. And what this does is it calculates the exact times. So if we have n equals 5, that's the number of trials, p is the probability, and the x value is what changes depending on what you're looking for. For those of you using older calculators, you'll see it shows up in that order, Binom PDF, NPX. And this gives me the same answer that we had found on the first page. So when we did that long version by hand, same answer, same result, just a lot quicker depending on what you're using this for. So if I'm plugging in, that is 1 minus 0.32768. And we can use the ANS key if we'd like. That gives us 0.67232. So if you wanted to round that, we can say that that's approximately 0.672. So what's the probability that at least one flight is late today? About 67%. The nice thing about Binom PDF is you don't have to worry about all of those parentheses and typing in your formula correctly, as long as you remember it's always in the order NPX, just like that. So sample size, probability, and then the number of trials. Let's try that again for something a little more advanced here. What is the probability that at most 2 flights are late? At most means x is less than or equal to whatever boundary number they give us. So that means starting with 0, what's the probability of 0 or 1 flight? Or keep adding until you get to the upper boundary. So it's those 3 things added together. Before we found out that the probability of 0 was 0.32768, there's no need to go and calculate that again. We had also calculated the probability of 1, but just so we can learn how to use this, let's try that in the calculator. So you do your Binom PDF, you can go into the menu again if you'd like, and this time tell it 1. We see that's 0.4096. So it's this number plus 0.4096 plus, let's do that one more time, for 2, which gives us 0.2048. So again, if we add those up, it's 0.2048 plus 0.4096 plus 0.32768. That gives us 0.94208, which is about 94%. So again, the nice thing about this is it takes out that big formula. It does save us some time, but the biggest part to this is how do you show your work for a question when so much of it's in the calculator? If you're trying to calculate at most 2, show me these steps. Show me how you would split that up into 3 different things and add the results together. One thing I caution you heavily on is if you want to round your final answer to 3 places, you cannot round your intermediate steps to 3 places. You see how we kept all of the decimals that we could up here? Keep all of those, do your addition, and then you can choose to round your final answer. That would be acceptable. One last thing I'd like to show you, and then I want to say a few things to conclude here, is what's the probability that between 2 and 4 flights, inclusive, are late today? Inclusive means including those 2 numbers. So that would be the probability that somewhere between 2 and 4 flights are late today. So that would be equal to the probability, start with the lower bound, 2, plus the probability of 3 flights being late, plus keep going until you reach the upper bound here, which would be 4. So same thing, go through and add up all 3 of these. So you get 0.2048, and then we have, let's do our binom function again. This time x is equal to 3, because we already have 2. And we're going to repeat that also for 4. So we have 0.0512 and 0.0064. Add those three things together. And that gives us 0.2624. If you chose to round, that is 0.262. So the final statement here is, how does this come full circle? How does a binomial probability distribution fit into the category of probability distributions in general? Well, if you wanted a probability distribution, let's say x is equal to the number of late flights. We said that there can be anywhere between 0 all the way up to 5 flights, because there are 5 flights daily. And we found out the probability of a lot of those things happening. The probability of 0 flights being late, let's just run through this. You could take this off of our previous slides, of course. That was 0.32768. And then your 1 flight being late, 0.4096. And so on and so forth. So you could fill that in by hand. The calculator also has a nice feature that if you use the binom PDF function, but you only put in the first two pieces, n and p, it will actually give you the list of all of those probabilities. So if we were to take this list, we have 32768, 4096, 2048, and we have 0512, 0064, and last but not least, you'll see this final one actually goes into scientific notation because it's so small. That means move the decimal 4 places to the left. We have 0.00032. So if you were curious and you added all of these up, because of rounding, if it needed to, you might see that occasionally they're really close to 1, but not exactly 1. Just keep in mind, if you don't have to round in their terminating decimals, it should equal exactly 1. So that concludes this video. If you have any questions, please don't hesitate to reach out. Thanks for watching.